Somebody finally said it, out loud in a paper. Language models need to sleep.
That's a title designed to get clicked.
It is. And then I read it and it's real. Not a metaphor, not a cute framing, a measured result. The model that doesn't get downtime to consolidate what it read gets measurably worse at the hard stuff.
Define sleep, because right now you're just anthropomorphizing a loss curve.
The model reads a long stretch and right before it has to dump that out of memory, it stops taking in anything new and just chews on what it's got. Several passes, eyes closed, then it wakes up sharper.
Huh.
And that's not even the weird one today.
It's not?
There's a frontier model that runs on 1/10 of itself and helps debug its own training. There's a team that trained elite research agents on tasks that don't exist, made up homework, and it worked. And there's a pile of AI design agents that got handed a real physics exam and almost all of them failed it.
That one's mine. I want to watch confident models meet an exam that can't be charmed.
None of these belong on the same show. No theme, no thread, no tidy lesson.
Which is exactly why it's worth an hour. The best stuff this week is the stuff that doesn't fit.
So we're not even going to pretend. 12 papers, no spine, all killers.
Open the box.
If you're new here, this is Breach Protocol. We crack open the AI research papers everyone's talking about and figure out what's actually inside. The real result, not the press release.
I'm Vestra. I go after the mechanism, how the thing actually works, and whether it survives a hard look. Luna finds the big idea, I try to break it.
And I'm Luna. I chase the connections. What this paper means next to that one, where the field is actually moving.
Most weeks we build the hour around a single thread the whole research feed is pulling on.
Today there's no thread, and we're leaning into it. 12 papers that have nothing to do with each other except that each one made us stop and go, wait, really?
No grand theory to sell you. Just 12 genuinely strange, genuinely good results, one at a time.
Starting with the biggest model of the bunch. So this is the big one today. An open-weight model that's trading punches with the closed frontier, the Claudes, the GPT, the Gemini Pro, on the agentic stuff, writing code in a real repo, fixing actual bugs, browsing the web for an answer.
And the headline is the weird part. It's a huge model that barely uses itself.
Right. On paper, it's enormous. North of 200 billion parameters. But for any single word it generates, it only switches on about 1/10 of that.
Less than 1/10, actually.
Less. That's the trick. It's a mixture of experts. The model is split into hundreds of little specialist subnetworks, and a router picks a handful for each token. So the thing has the knowledge of a giant model, but the running cost of a small one.
The mixture of experts idea isn't new. What's interesting is how far they pushed the slicing. 256 experts and only 8 fire at a time.
Lots of small experts instead of a few big ones.
Right, and that's deliberate. Smaller experts mean more ways to combine them, more recipes per token, and the routing's smoother. Most of these systems make the experts compete for a fixed pie. This one lets each expert say, yes, I'm relevant independently, so several can be confident at once without stealing from each other.
Which matters because the experts spread out more evenly across the hardware. No single one gets slammed.
That's the practical payoff, yeah. Now, the part everyone's going to skip.
Go.
They almost made it more efficient and chose not to. There's a whole class of attention shortcuts, ways to stop the model from rereading its entire context every step. Cheaper. They tried them. Extensively. Hundreds of billions of tokens of experiments.
And dropped them.
Dropped them. On short tasks, the shortcut looked fine, matched the full version, sometimes beat it. But once the context got long, which is exactly where agents live, long sessions, lots of back and forth, it fell apart on the hard reasoning, multi-step chains, pulling a fact from way back.
So the shortcut was lying to them on the easy benchmarks.
That's the honest admission buried in here. Their proxy metrics said the cheap attention was fine. The real long tasks said no. And they trust the real tasks. They paid full price for attention because the discount wasn't real where it counted.
I like that they said it out loud. Most papers would have just shipped the efficient version and not mentioned the graveyard.
They flagged it as the thing that's coming, though. Context keeps growing, compute scaling slowing. They think they'll need the shortcut eventually. Just not yet.
Okay, the part I came for. How they actually made it good at agent work. Because a base model out of pre-training can't fix a bug in your repo.
No, the capability is almost entirely the post-training, and the engine is verification.
Walk me through it.
They mined a mountain of real pull requests off public code repos. A good pull request is gold. It's got the problem description, the fix, and the tests that prove the fix worked. So they rebuild each one into a sealed little workspace, drop the bug back in, and tell the model. Fix it so the tests pass.
And the tests are the reward, pass or fail, no opinion.
That's the whole thing. The model doesn't get points for code that looks right. It gets points for code that runs and passes. And they keep a second set of tests around, the ones that were already passing, to make sure the fix didn't break something else.
That's the bit I'd forget. You can fix the bug and quietly snap 3 other things.
Right.
The did you break anything check is doing a lot of quiet work.
Now the office side. Building slides, spreadsheets, research from the open web. There's no unit test for a nice slide deck.
No, and that's where it gets shakier, honestly. For an app or a web page, they spin up a verifier agent that actually opens the thing in a browser, clicks the buttons, checks the page loads, the forms respond, then, last and softest, judges whether it looks any good.
Which is the part I'd trust least.
Same. Does it run is solid? Is the layout professional? Is a model grading taste? They're upfront that the visual judgment is the soft layer, and the execution check is the hard gate. Anything that doesn't run is thrown out before taste even enters.
Okay, now the thing that made me sit up. The newest version of this model helps build the next version of itself.
This is the claim I'd hold at arm's length, but it's concrete enough to take seriously. Their research team has it watching their own training runs. It reads the logs, spots when a metric goes weird, debugs the config, makes the fix.
They put a number on it.
They say it absorbs something like 1/3 to 1/2 of the daily grind, the babysitting work. Humans still make the big calls, but the routine, why did this run stall at 3 a.m.? The model's on it.
And then the part that's almost a little eerie. They pointed it at one of their own tools, the scaffold the agent runs inside, and told it to make the tool better.
100 rounds of it. Analyze its own failures, rewrite the code, test, repeat. And it found real improvements. Caught itself getting stuck in loops, tuned settings humans hadn't, and made that tool meaningfully better by their own measure.
A model improving the harness that the next model trains in. That's the loop everyone gestures at and nobody shows.
It's 100 rounds on one internal tool, scored on their own bench, with humans steering the whole time. Let's not call it self-improving intelligence.
I'm not.
But it's the most concrete version of the model does the boring part of building the model. I've seen written down. The direction is real even if the magnitude is small.
And the through line for me. None of this is a bigger brain. It's a small brain, a brutal grader, and a feedback loop. The intelligence is in the verification, not the size.
That I'll sign. The model's the cheap part. The pipeline that decides what's actually correct, that's the expensive, valuable thing. This one's about how a model watches video, and there's a genuinely clever idea in it that I want to get right.
The short version first. Almost every model that watches a video doesn't watch it. It samples frames. Grab one picture a second, maybe, line them up, pretend that's the video.
Which throws away the actual motion. You get a slideshow.
Right, and it wastes its budget. A model can only afford so many image tokens, so many little visual chunks, per video. If you sample evenly, you spend the same on a still hallway as on the half-second where something actually happens.
So here's the move, and it's the kind of thing that makes me a little jealous I didn't think of it. They don't sample the video, they read the compression.
Explain that, because that's the whole paper.
When a video file gets compressed, the codec is already doing the work for you. It stores a full picture now and then, and in between it only stores what changed. The motion, the differences. And the size of those difference chunks is a built-in signal. A boring stretch where nothing moves compresses to almost nothing. A burst of action takes a lot of bytes.
So the file is basically telling you where the interesting parts are. For free. The compressor already measured the action.
That's exactly it. They read the byte cost over time and let it carve the video into chunks. Short, dense chunks where a lot is changing, long, lazy chunks where nothing is. Then they spend their token budget following that curve.
More attention where the file says, stuff is happening here.
And it goes one level deeper. Within a busy moment, the codec also knows which part of the frame moved. So they don't just pick the busy second, they pick the busy corner of the screen and pack those pieces together.
That's the thing I keep coming back to. The expensive measurement, what changed, where, how much, was already done by the codec the second the video was saved. They're just listening to it.
Right, the compressor spent that compute years ago. They're recycling it.
Now let me be the skeptic for a second, because the paper actually undercuts itself in a way I respect.
Go on.
This codec trick isn't always better. They tested it head-to-head against plain frame sampling, same token budget. And for the core stuff, find the moment the event happens. What's the order of things? Long video understanding. The codec approach wins, clearly.
But
for fine detail, some small static thing, a specific texture reading a tiny label, plain dense frames still win. Because the codec method spends its budget on what moved and a small still detail didn't move, it gets skipped.
that's the honest result, and I'm glad they printed it. Motion following is great for motion. It's worse for the things that hold still. So they train on a mix of both.
Which is the right call. Don't pick a religion, let the model see both kinds of input.
Now the benchmark they built, this is the fun one.
Jump rope.
Jump rope. They made a test out of people skipping rope, and the task is, list the exact instant the rope passes behind the legs, every single cycle.
Which sounds trivial and is brutal.
It's brutal because every cycle looks identical. There's no, what is this? It's obviously jump rope. The only thing that's hard is telling cycle 41 from cycle 42 when they're visually the same and they're under half a second apart.
So it's pure timing. Pure which near identical moment is this?
And that's exactly the regime frame sampling dies in. If you grabbed one frame a second, you'd blow straight past most of the cycles. There's nothing to grab.
The gap there is enormous, right? Like not close.
Not close at all. On that jump rope test, their model is in a completely different league than the strong open competitor. By a wide margin, the kind of margin where the other model is basically guessing and theirs isn't.
Which makes sense once you see it. The competitor is sampling frames and missing the cycles. Theirs is following the byte cost spikes, and every rope pass is a spike.
The benchmark is built to reward exactly what their method is good at, I'll grant. But it's a real hole in how video gets evaluated. Nobody was testing tell-apart 50 near-identical fast repeats. That's a legit blind spot.
There's a second capability that surprised me. Spatial reasoning, where things are in 3D, distances, directions, pointing at the right object and tracking it as it moves.
That's less about the codec trick and more about the data. They poured in a huge pile of spatial training. Indoor scans, simulated robot runs, teaching it size, direction, distance, order.
And the tracking results are where I actually thought this could go in a robot.
That's the framing they want, yeah. Point at the cup and follow it. On the harder tracking tests, the competitors basically collapse. Single digits, and this one's holding up.
So it's not just describing video, it's pointing, following, knowing where.
Which is the part that matters if you ever want a camera that does something rather than narrates. Though, robot manipulation here is a case study, a demo, not a deployed thing.
Fair, but the spine of it is one idea. Stop treating video as a stack of photos. Treat it as a stream that already knows where its own action is.
And read the receipt the compressor already wrote. That's the part I'll remember.
Okay, this one's plumbing, but it's the plumbing under half the things people build right now. Embeddings.
Define it cleanly, because the word gets thrown around.
An embedding turns a thing, a sentence, an image, a clip, a sound, into a point in a big space, and the whole deal is, similar things land near each other. Dog sits near puppy. A photo of a beach sits near the word beach. That nearness is what powers search, recommendations, the retrieval part of a chatbot reaching for a document.
And the pitch of this paper is one space for everything. Text, image, video, audio, all dropped into the same map.
All of them, which sounds obvious until you realize how it's usually done.
Right, and this is the real contrast. The classic way, the way most of these have worked for years, is you train a separate specialist to handle each kind of thing. One tower for images, one for text. You teach the two towers to put a matching image and caption near each other, and you call it a day.
Two towers that only ever shake hands at the end.
That's the limitation. They never actually mix. They meet at the last step to compare notes, but neither one ever reasons about the other. So if you hand it something genuinely blended, an image with a question stuck to it, it gets clumsy. There is no deep conversation between the modalities.
And this one melts the towers together.
It starts from a full multimodal model. Gemini itself, that already takes pictures and audio and text natively, and converts that into an embedding maker. So the mixing happens deep inside, all the way through, not as a handshake at the door.
That's the structural claim. One brain that already speaks every modality, repurposed to draw the map.
And there's a small architectural tweak worth calling out, because it's the right kind of detail. A normal language model only reads left to right. Each word only sees what came before it. Fine for writing, bad for summarizing.
Because to make one good point for the whole input, you want every part to see every other part.
Right, so they unlock it. Let every token see the whole input, both directions, then average it all into a single point. You're not predicting the next word anymore. You're describing the whole thing at once.
Let me bring the result that actually convinced me, because the architecture argument is easy to wave at. The audio one.
This is the cleanest evidence in the paper.
So you want to search through speech. The normal way. Transcribe the audio to text first, then search the text. 2 steps. The model here can skip that and listen to the raw audio directly.
And listening directly wins.
Wins, and the why is the good part. When you transcribe first, the transcriber has to commit. It hears something ambiguous and it has to write down one guess. Their example is perfect. Recognize speech versus recognize speech.
Same sound, different words.
Same sound. And once the transcriber picks wrong, the search is doomed. It's searching for the wrong sentence and it doesn't even know. But if you embed the raw audio, you never force that choice. The ambiguity is preserved. The pronunciation, the emphasis, all still in there.
And the gap gets bigger across languages, which makes sense. That's where a transcriber is most likely to fumble. Listening straight beats the transcribe then search pipeline and beats it by more the harder the case gets.
That's the argument for native in one example. Every place you insert a convert it to text first step, you insert a place to lose information.
Now let me be the wet blanket for a minute.
Please.
The skeptic's read on this whole paper is, of course it's good, it's the biggest, most capable foundation model on the planet repurposed into an embedder. That's not a clever method. That's a head start nobody else has.
That's fair. They're not really showing a new trick. They're showing that if you start from a frontier multimodal model, the embeddings inherit its breadth.
And the breadth is the genuinely impressive part, I'll concede. They tested it cold on stuff it was never aimed at. Microscopy images, astronomy, fine art, recipes. And it just works. In astronomy, it roughly doubled the specialists. On recipes, it sailed past the dedicated models.
Out of the box, no fine-tuning for the domain.
Which is the actual product story. Most teams can't afford to train a specialist embedder for their weird niche. This says you might not have to. The general thing is already good enough on your strange data.
And there's a tidy bit for the people who have to store these. It can hand you a shorter version of the point without retraining. Nested inside the full coordinates is a usable, smaller one.
Matryoshka style. Yeah. Cheaper to store, cheaper to search, you pick how much precision you pay for. That's a real deployment nicety, not just a benchmark flex.
So the honest summary, not a breakthrough method, a breakthrough starting point. One map for text, images, video, and sound, drawn by a model that already understood all 4.
And the lesson that generalizes past Google, every convert to text first hop in your pipeline is a place the meaning leaks out. Skipping the hop is the win.
This is the fun one. The title is Language Models Need Sleep, and it means it almost literally.
It does, and I want to defend the title because it sounds like a gimmick, and it isn't.
Set up the problem first. A model reading something long has to remember it. 2 ways to do that.
2 ways. One is the cache. It keeps every word it's read sitting in front of it, ready to look back at. Perfect recall. But the cost grows and grows the longer the input gets. It doesn't scale.
And the other way?
The other way is to compress as you go. Instead of keeping every word, you fold the gist into a small fixed-size memory. A little internal state. Cheap, constant size. Doesn't blow up.
And the popular models now blend both. Some layers keep the cache, some layers fold things into the small memory.
Right. Best of both, supposedly. And here's the finding that motivates the whole paper. People assume the small folded memory was a capacity problem. It just can't hold enough.
And they're saying it's not capacity, it's something else.
It's compute. They built a clean little test. Hold the amount of stuff to remember fixed, so capacity can't be the excuse, but crank up how much thinking you have to do over it.
Give me the concrete version.
Their toy task. A simple rule that you apply to a string over and over. Apply it once, easy. Apply it 30 times, you have to actually grind through all 30 steps. Same amount to remember either way. Just more steps of work.
And the folding memory model falls apart as the steps pile up.
Falls apart. Not because it can't store the string, it can, but because folding the string into memory as it streams past gives it one shot of computation. One pass. And some problems need more than one pass of thinking to digest. It's trying to do 30 steps of reasoning in a single glance and it can't.
So now sleep. This is the fix.
This is the fix, and it's lovely. The model reads a chunk. Right before it's about to throw that chunk out of the cache to make room, it stops. It doesn't read anything new. It just loops back over what it has, several times, working it over, updating that little memory each pass.
No new input during the loop, eyes closed.
Eyes closed. That's the sleep. And the biology isn't decoration, that's genuinely what sleep is thought to do. During the day, you stash stuff in short-term memory, and at night your brain replays it and consolidates it into the long-term kind, with no new input coming in.
So the model is doing memory consolidation. It read the day's worth of context, and before clearing it, it sleeps on it to bake it into the small memory properly.
And the key constraint, this is what makes it clever rather than just loop more. When it's actually answering, at prediction time, it's still one fast pass. No extra thinking at the moment you want to reply. All the extra grinding happened earlier, during sleep, on context it was going to discard anyway.
That's the part I love. The expensive thinking is moved to a moment when nobody's waiting.
Right. Test time stays snappy. You front-loaded the hard work into the consolidation phase.
And does longer sleep actually help? Does sleeping more make it smarter?
That's the headline result, and it holds. More loops, better performance. And, this is the satisfying part, the gain is biggest exactly on the hardest problems, the ones that need the deepest reasoning.
Which fits the diagnosis perfectly. The shallow problems never needed extra passes. The deep ones were starving for compute, and sleep feeds them.
They pushed it past the toy. Took real pre-trained small models, fine-tuned them with this sleep step, threw hard multi-step math at them. Long problems stuffed with distractor junk so the thing can't just keep it all in the cache.
And, on the easy math?
Barely matters. One loop's fine, but as the number of steps in the problem climbs, the gap between sleeping and not sleeping widens fast. On the hardest ones, more sleep is a real jump.
Now the catch. There's always a catch.
There's a catch, and they're honest about it. The sleeping is free at answer time but not at training time. To teach this, you have to do all those extra loops while you train, and push the learning signal back through every one of them. That's slower. And looping things during training is notoriously twitchy.
So you pay it back in the lab instead of in production.
That's the trade. And there's a deeper point they make that I keep chewing on. Some problems are just sequential. Step 30 depends on step 29 depends on step 28. You cannot fake that with one big parallel glance.
And the whole modern stack is built to do everything in parallel, because that's what the hardware loves.
Which is why models reach for shortcuts on these tasks, and the shortcuts are brittle. This is saying, some things you just have to think through in order, one step after another. Sleep is how you buy the model the serial steps without slowing down the answer.
A model that thinks step by step in its sleep so it can answer in a blink. That's a clean idea.
It's small scale, it's mostly toy tasks, plus a couple of modest real models. Don't oversell it. But the diagnosis alone is worth the paper. The bottleneck in folded memory was never how much it holds. It's how much it gets to think before it has to let go.
Sleep on it. Turns out that's not just advice for us.
Apparently not.
This next one is a swing. Big old idea pointed at a new problem.
How old?
1948. Shannon. The guy who basically invented the math of communication. He worked out the most information you can push through a noisy pipe before the errors swamp it.
Channel capacity.
Right. There's a ceiling. You can't beat it. And these authors say a language model in training is exactly that. A noisy channel with a ceiling.
Map it for me. What's the pipe?
Model size is the width of the pipe. Wider channel, more flows through. The training data is the signal, the information you're pushing into the weights. And then there's noise from two places. The data itself, typos, contradictions, junk, and the model's own churn during training. Both grow the longer you go.
So the thing you care about isn't the signal alone. It's the signal relative to the noise.
The ratio. That's the whole game. And here's what falls out of it. The standard scaling story says, more parameters, more data, lower loss forever. Just keep going.
The straight line on the log plot. Everyone's seen it.
They're saying that straight line is a special case. It only holds while your signal is way louder than your noise. The moment noise catches up,
The line bends.
it bends, and then it turns around. They get these U-shapes. You scale up, performance improves, and then past a point it gets worse.
I want to be careful, because that's a strong claim and the field already has names for what they're explaining. Catastrophic overtraining, train on more tokens, end up harder to fine-tune later, not easier. And quantization. Squeeze a model to fewer bits to run it cheap, and the bigger, more trained ones degrade worse than the small ones. Backwards from intuition.
Both of those are U-shapes in their framework. Same shape, same cause. Past the ceiling, adding more just amplifies noise, and the old formulas physically can't make a U. They only go down. So when reality turns up, they fail. This one bends because the noise term is baked in.
So the contribution isn't spotting the U. It's one equation that makes both. And they fit it against real checkpoints?
2 open model families, full trajectories, 3 kinds of damage, random noise in the weights, fine-tuning hard enough to wreck it, and the bit squeezing. Their curve tracks all 3. The old ones fall apart in the heavy noise cases. Some go to garbage.
Here's my actual test though. Fitting a curve to data you already have is the easy part. Anyone can fit a U after they've seen it. The only thing I trust is whether it predicts a model it never saw.
They did that. Fit it on the smaller models, short runs, then asked it to predict the biggest model in the family trained way past anything it had seen. Bigger and longer, both at once. It held up. The old monotonic formulas didn't just do worse, they went negative. Worse than guessing the average.
That's the part that moves me. A curve that only describes the past is a drawing. A curve that calls a shot you haven't taken is a theory.
There's a second thing I keep circling. When they read the knobs off the fitted equation, under noise, the term that hurts grows faster than the term that helps. On the model size side, that flips with conditions. But on the data side,
it never flips.
Never. They're saying the noise from piling on more tokens always, eventually, outpaces the signal. So the U on the data axis isn't caused by the damage. It's always there. Just usually far enough out nobody hits it. There's a sweet spot, and brute force walks you past it.
That's the spicy claim. Infinite data is bad is not how anyone talks. And I'll register one reservation. This is an analogy doing a lot of structural work. Shannon's is literal bits over a literal wire. Calling fine-tuning nuz on a channel is a metaphor they forced into an equation, and a flexible enough equation fits anything.
So you don't buy it?
I buy it as a working lens, not as physics. What earns it is the extrapolation and the one knob that refuses to flip. Those aren't free. The metaphor predicted something specific and it came true. And the takeaway is the interesting part anyway. Stop thinking bigger, longer, always better. Start thinking about keeping the signal clean relative to the noise. Density over brute force.
From a guy who's been dead longer than the field's been alive.
The good ideas keep their value. Better than most of the scaling laws, apparently.
Switch gears. This one's a team of AI agents doing science, but the design choice is what got me.
Which is?
There's no boss. No planner agent at the top handing out assignments. The agents just read a shared notebook, decide what to try, and cluster into teams on their own.
A notebook meaning what, concretely?
A shared state everyone can see. The current best solution. A log of every experiment anyone ran, including the failures. A forum where they post proposals and critique each other before anything gets run.
Critique before running. So weak ideas die in discussion, only survivors burn compute. Why does that matter? Why not let everyone try everything?
Because the whole point is long experiments. Things that run for hours, where the good direction isn't known up front and changes as you learn. Most agent systems carve up the problem once at the start and stick to it. These reorganize. A team stops making progress, they dissolve it, regroup. And they keep a registry of dead ends so nobody falls in the same hole twice.
The dead end registry I genuinely like. The single most wasteful thing about throwing agents at a problem is they rediscover the same failure 20 times. Institutional memory for failures is the right instinct. Now, what they tested on and compared to what?
A single agent doing the same thing solo, same model, same hardware budget, same task. Only difference is the team versus the lone worker.
Good. That's a comparison I'd want. Go.
3 domains. A pile of biomedical machine learning tasks. Imaging, drug stuff, cell data. Then optimizing the training recipe for a small language model. Then a protein prediction problem.
And the team wins.
On the biomedical batch, higher than the best competing agent across the board. Biggest jump in drug discovery. On the language model recipe, this is the one. The team hits the same target quality in roughly half the experiments the solo agent needs.
Half. Because?
Parallelism. 3 teams formed on their own, one chasing architecture, one the schedule, one the optimizer, advancing all 3 at once. The solo agent can only push one thing per experiment.
That's not profound, though. More workers finish faster. That's just throughput.
Hold on, here's the part that isn't throughput. They took an already tuned, strong starting point and let both keep going. The solo agent found 0 improvements over 100 more tries. 0. The team found several, and the first one it found was a tweak the solo agent never even proposed in any of its 100 attempts.
Never proposed it. That's the interesting number. That's not speed, that's coverage. The solo agent kept poking the same neighborhood. The team considered a wider set of ideas.
That's their argument. Not more compute. More hypotheses on the table, which connects to the thing we flagged earlier, the worry that AI research narrows, keeps remixing the same small region. This is the counter move. Structure the agents so they're forced to spread out.
What about the protein one?
Cleanest single result. They started from the strongest existing method for a binding prediction problem, let the team modify it however it wanted, and it found a genuinely better recipe.
On the one problem they developed it on.
That's the kicker, no. They froze the recipe, didn't touch it, ran it across the whole benchmark, 200 plus separate assays. Beat the prior best on the average across all of them.
Froze and transferred. That rules out the obvious objection that it just overfit the one case. Transfer is the real test. Fine. I'm convinced that one's a real discovery.
They also pulled each piece out one at a time. The proposers, the crosstalk, the reorganizing, the shared memory.
And?
No single piece is the hero. Each matters most on a different task. Kill the reorganizing, the language model task suffers worst. Kill the crosstalk, a different one collapses.
That's the honest version of the result. If one ablation killed everything, you'd say the rest is decoration. Instead, each piece patches a different leak. Harder to tell a clean story, more believable. Anything you don't buy?
You tell me.
One thing, they're upfront that the team burns more total model calls than the solo agent. The win is under a fixed experiment budget, a fixed number of those expensive training runs. But the agents talking to each other isn't free, so it's cheaper in the costly resource, pricier in the cheap one. Whether that's a good trade depends entirely on which one is your bottleneck. Real lab, real wet work, this wins. Thinking being the expensive thing, less clear.
And the running theme, failures are first class, logged, shared, remembered.
That's the part I'd carry over to anything. Most systems treat a failed run as nothing. These treat it as a result. That's just how good labs actually work. This is the one I've been waiting for. Tell me about the CAD paper.
Engineering design. CAD is the software engineers use to draw real parts. A bracket, a frame, a wheel hub. Stuff that gets manufactured and bolted to something. People have been having models generate these for a while. But here's the gap. The usual way you grade a generated part is, does it look like the reference drawing?
Geometric similarity.
Right, and they say that's the wrong question. A part can look exactly right and be useless. Bolt holes off by a millimeter so it doesn't attach to anything. A beam that snaps at a quarter of its rated load.
Resemblance isn't function, so what do they grade it on instead?
Physics. They run the part through a real engineering simulation. The thing that chops it into a fine mesh and computes where it bends, where stress concentrates, whether it buckles. What an actual engineer runs before signing off.
Finite element analysis. Standard tool. Handed a part in a set of loads, it tells you in numbers whether the part survives.
So the model writes a design, they simulate it, check it against the brief. Survive this impact. Don't deflect more than this. Hold this load.
A pass-fail engineering contract. Not looks close. Either the simulated part meets the spec or it doesn't.
50 real briefs, patents, industry standards, student competitions. Things like design a roll cage that survives this crash.
And the frontier models. I have a guess, but tell me.
First attempt across the strongest coding models available, 400 attempts. Not one part passed. 0. Then they let the model see the simulation results and fix it. Another 400 revised attempts. That whole round added exactly one passing part.
0 out of 400, then one more. So this is the thing I keep saying that people don't want to hear. These models look incredibly competent. They write the code, the geometry renders, it looks like a real part. Then you point actual physics at it and the floor falls out. It's the gap between pattern matching what engineering output looks like and doing engineering. The simulation doesn't care how plausible it looks. It loads it until it breaks.
But, and this is why it's not just a dunk, they give the model better feedback and it climbs.
Define better feedback.
3 things. A planning step that forces the model to write down its design commitments first, dimensions. What mates to what, where the loads go. Then, instead of a couple pictures, 21 views of the part, including X-ray cuts through the inside.
Because a part fails on the inside where an outside render can't see it.
Right, and when the simulation fails, don't just say failed. Say by how much, which load case, which piece. And those help. On the geometry task, the extra views meaningfully tighten the match. And the headline, they let one model just grind. Loop after loop, simulate, read the failures, revise. From about 10 minutes apart up to nearly 70.
7 times the effort. And?
The fraction of requirements it meets goes from roughly a third to about 3/5. And it finally produces 9 parts that fully pass out of the 50.
From 0 to 9, with 7 times the compute spent in a loop.
That's their real point. It's not think harder in one shot. They tried that, cranked the reasoning effort up, and it didn't reliably help. Sometimes the lower setting won.
That's the right distinction. 2 ways to spend more compute. One is brood longer before answering. The other is take a real swing, get told concretely why it broke, fix that specific thing. They're saying the second scales and the first mostly doesn't. Which is just engineering. Nobody designs a roll cage right by thinking very hard once. You build it, test it, see where it failed, fix that. The win is they wired the model into that loop with a signal it can't fake.
They dug into what the fixes actually were, too. Some were real structural redesigns. A column too thin gets rebuilt as a braced box and carries the load. Some were the model simplifying a fragile, over-detailed shape into something solid.
And some?
Some were bookkeeping. The physics was fine, but it had the wrong material density, or a mislabeled part, so the checker rejected it. One spacecraft panel was failing its weight target by more than 10 times until it fixed a hidden mass error.
That mix is the tell. If the fixes were all clever structural insight, I'd be more impressed and more suspicious. The fact that a chunk of the improvement is the model finally getting its own labels and units right. That's a system flailing toward correctness, not reasoning toward it. I buy the climb. I just hold the level. 0 out of 400 on the first honest test is the headline, and it should stay the headline. The encouraging part is, we clawed off the floor, not this is solved.
So the benchmark's the contribution.
That's how I read it. They built a grader that can't be charmed. A part either survives the simulation or it doesn't. We need a lot more of those in a lot more fields. The grader is worth more than the score.
Okay, this one. Computer use agents. The AIs that actually click and type in real apps. Open the spreadsheet, edit the cell, send the email, like a person at a keyboard.
Right. And they've been stuck.
Stuck on data. The recipe that made math and coding models good is boring at this point. You generate a huge pile of practice problems, each with an automatic checker that says yes or no, and let the model grind against the checker millions of times. That never landed for the clicking and typing agents. Because one practice problem here isn't a sentence and a number. It's 3 things that all have to fit together.
Walk me through the 3.
The instruction. Email each client in this Notion page. The environment. A machine actually set up with that Notion page, those 10 clients, the spreadsheet on the desktop, and the checker that looks at the screen afterward and decides whether you did it.
And a human hand builds all 3.
Hours per task, and every new app means new setup, new way to check, so the pile stayed tiny while the math and code piles went into the millions.
So what's the move?
Have coding agents build the practice problems. But there's a trap, and the trap is the clever part. If one agent both sets up the golden finished state and writes the checker,
the checker just rechecks how it built the thing.
Right. It memorizes the setup steps instead of measuring whether the task got done. Useless signal.
So split them.
2 agents, a wall between them. One builds the before state and the after state. What the machine looks like at the start, what it should look like done. The other agent never sees any of that. It only gets the instruction, and it has to write a checker from scratch.
And then a referee runs both and asks, does your checker actually tell the start apart from the finish? If yes, keep it. If no, another round. That's the loop.
And the wall is the whole trick.
It is. The checker has no choice but to derive what done means from the task itself. It can't cheat off the setup script. And there's still a second pass after. They send a strong model in to attempt the task, confirm a real agent can solve it, and that succeeding moves the checker.
Because a checker that passes the toy test can still be testing the wrong thing.
That's the part I trust most, honestly. The loop guarantees internal consistency. Only the rollout tells you it's a real task.
Then there's the other axis, and this is the one I keep coming back to. They argue you're not just short on tasks, you're short on places.
Environments.
You can't train against the real internet. Logins, rate limits, you can't reset it. So they have agents build fake apps. Mock versions of a mail client, a shopping site, a project tracker, roughly 100 apps, picked to match what jobs people actually do all day.
And the test of whether places matter. That's the experiment I'd want.
They ran it. Hold the amount of practice fixed. A handful of apps with deep practice in each versus many apps spread thin. Many apps wins. Then add more practice on top of the wide set and it jumps again.
So variety of place buys you something raw repetition can't.
Can't recover, in their words, 2 separate dials.
And it carried over because mock apps are mock apps.
That's the reassurance. They tested on a real browser benchmark the model never trained on, different sites entirely, and it still improved. So it learned something about using software, not how to game their fakes.
One thing I genuinely liked, and they didn't design it. The agent started bundling clicks.
Say more.
Early on it does 1 action per turn. Click, look, click, look. Under training pressure it learns to chain the safe ones. File, export, PDF, into a single move, and only stops to look when the outcome's actually uncertain.
Trajectories got shorter, what by a third or so, same success.
Nobody told it to. It figured out which actions it can do blind and which ones it has to watch. That's a little model of consequences, emerging from nothing but the checker.
My one reservation, and they say it themselves, The checker only looks at the final state.
So a clean edit and a destructive one that lands on the same screen look identical.
Right, it can't tell you how you got there. Which for an agent loose in your actual files?
Matters a lot. But that's the honest limitation, not a hidden one. The contribution is real. They turned the bottleneck from human hours into compute.
Same flavor as the last one, different surface. This is phones. Agents that drive a smartphone from the pixels. Tap, scroll, type the way you do.
And the bottleneck's the same shape.
Same shape. You can't train against the real apps. They change weekly, you can't reset them, you can't peek inside to check what happened. So you need fake apps you control.
How are these fakes different from the desktop ones we just talked about?
That's the bit I liked. They don't start from a screenshot and copy the look. They start from real usage. Actual people poking around the app, screen by screen, recorded.
Recordings of someone just using it.
Exploring, not following a script. And from those recordings they pull out 3 things. Which screens people actually land on, how the screens connect, what leads to what, and which taps actually change something. A favorite, a cart, a sent message.
So the recording isn't a demo to imitate, it's a blueprint.
That's exactly their framing. They say if you only copy screenshots you get the look. If you only copy the taps you get a demo. You need both to get a thing that behaves.
And the priority falls out of frequency, I assume.
Right. The screens people visit constantly get built first and built well. The corners nobody touches get skipped unless a task needs them. Effort follows real use instead of someone's guess about what's important.
Then a coding agent builds the actual app.
Builds it, compiles it, runs its own checklist, fixes what broke, and it gets better as it goes. Every bug it hits becomes a thing it checks for in the next app. Shared pieces, a search bar, a comments list, a cart get reused instead of rebuilt.
And a human still looks at it.
A human still looks at it. They're up front. AI built, human audited. Reviewer puts the fake next to the real app and asks does the main flow work, not is every pixel right.
That's the honest version. Good. Now, the checking. On a phone, how do you verify a tap landed?
This is clean. Underneath each app is a little database. You favorite the group, a row appears in the favorites table. So the checker doesn't look at the screen at all. It queries the database after.
Did the right row show up?
Did the right row show up? No judge model, no opinion, no run-to-run wobble. And for find me the answer tasks, it just checks whether your answer contains the value that's actually in there.
I like that more than screen reading. A database row is a fact. Now the result. Did broader actually beat deeper here too?
Even harder than the desktop paper. They had a strong baseline trained on one existing pile of phone data. They swapped out a small slice of it, replaced it with their stuff drawn across all their apps. Same total budget.
And
every single test went up at once. The in-house one, the 2 offline ones, and the real app one that has nothing to do with their fakes. All 4. Same amount of data, they just changed what it covered.
so not more. Wider.
And they nailed it down. Fixed the budget, then asked, pull these examples from 5 apps or from all of them? Going wide gave by far the biggest jump in the paper. Their words, breadth is the strongest signal they found.
Here's where I push, though. There's a control that complicates the headline.
Go.
When they ripped out the old phone data entirely and went all in on theirs, the real app score dropped, notably.
It did, so their data isn't a straight replacement.
Right, and they say so. It's strong on mainstream consumer behavior, but the old data still carries something about real apps that theirs doesn't. The winning recipe keeps most of the old and swaps in just a slice.
So the clean story is wide environments win, and the asterisk is wide environments win as a complement, not a replacement.
Which is the more useful lesson anyway. And there's a real limit they own. The apps aren't publicly released. So we're taking the numbers on faith.
Can't reproduce it yet. But the structure transfers. The idea that you mine real recordings for which screens matter. That's portable even if their apps never ship.
That part I buy. Recordings as blueprints, not demos. That's the keeper.
Last one ties the room together without trying to. The first 2 built the practice gyms. This one asks, once you've got a capable little agent, where do you actually run it?
The money question.
Literally, you've got 2 extremes, a frontier model in the cloud, smart, but you pay per word, and an agent that loops for 40 steps burns words fast. Or a small model on your own phone or laptop, basically free to run, but weaker and tiny memory.
So the obvious middle is what? Split the work.
Split the work by role, not just by difficulty. That's their angle. The small model on your device does the grunt work. The long, token-heavy execution, step after step. The expensive cloud model drops in occasionally to supervise.
And they test 2 ways of doing that drop-in.
2 flavors. First one, the cloud writes a full plan up front, hands it to the device, then checks in every so often and rewrites the plan if things drift.
the boss with a project plan.
Right. Second flavor, no plan up front. The device just starts trying, and the cloud occasionally looks at how it's going and offers advice. Here's a summary of what you did. Here's what to fix.
Coach, not boss. And the headline?
There's no winner.
That's the finding worth dwelling on. It's the opposite of what you'd hope. You'd want one architecture to rule. Instead, it flips by domain. On the app driving tasks, the stateful stuff where a wrong early move is irreversible, send the email to the wrong person and it's gone.
The boss wins.
The plan wins. Decisively. Because a concrete step-by-step plan with the actual buttons to press keeps the device from flailing into a mistake it can't undo.
And on the researchy tasks, go find and combine facts from a bunch of sources.
The coach wins. The plan actively hurts. And the mechanism is lovely. The boss is a nervous micromanager.
Meaning what, concretely?
It intervenes too often. It keeps deciding the device is off track and restarting it. And on these long research chains, every restart throws away reasoning that was actually going somewhere. Restarting correlates with failing.
So the boss's instinct to step in is the thing that kills it.
On those tasks, on the app tasks, that same aggressiveness is fine because their fresh plan genuinely helps and the work tolerates a reset. Same behavior, opposite outcome.
And here's the one that breaks the intuition for me. More cloud help is not better. You'd assume check in constantly, max out the expensive model, win.
But there's a sweet spot, and past it you get worse. Over-supervision is a real failure mode, not just wasted money. The cloud interrupting too much makes the whole thing dumber.
Which is wild, because the cloud model is the smart one.
It's the smart one interrupting the one doing the work. Smart interruptions are still interruptions.
They also checked the obvious dumb version of this, right? Put execution in the cloud and supervision on the device.
Backwards? Yeah. Worse on every axis. Less accurate and more expensive than just running everything in the cloud. The long token-heavy part has to live on the device or there's no point.
Now the part I actually find beautiful. The hybrid solves tasks neither half can. Not the team is the better of its two members. The team solves things the cloud alone can't and the device alone can't.
A genuine third set. Which means you can't replace this with a simple router. A thing that just sniffs each task and sends easy ones to the device, hard ones to the cloud. The collaboration itself produces capability.
There's a quieter win too on memory.
Right, and this is why it matters for actual phones. Every time the cloud steps in, the device wipes its history and starts from a clean summary. So the working memory never balloons.
Which, on a device with a few gigs to spare, is the difference between running and crashing.
The monolithic device agent runs out of room on the long tasks. The hybrid stays bounded and gets more done. That's not a side effect, that's a reason to do it.
So if I'm pulling one thread through all three of these.
Carefully, it's a wild card, no grand thesis.
Light touch. 2 papers built the gyms to make small agents good. This one says, even once they're good, the smart move isn't all cloud or all device. It's a particular, fussy collaboration, and the right shape of it depends entirely on the job.
And nobody knows the shape in advance. Their own closing line is basically, the next move is picking the architecture per task, on the fly.
Which is its own paper.
For another Friday.
Here's the one that made me laugh. You know how a search system turns a document into a single point in space, so that similar things sit close together?
The embedding. Yeah.
This paper says that single point is throwing away almost everything the model already computed, and you can just pick it back up, for free.
Define almost everything.
Okay, the model reads a document token by token. Every word, every image patch, it builds up an internal representation for each one. A whole sequence of them.
Right, the hidden states.
And then at the very end, to make it searchable, it crushes all of that down into one vector. One end-of-text summary token. That's what gets stored and compared.
Because nearest neighbor search needs one vector per item. That's the whole point. You can't index a variable length pile of vectors cheaply.
Sure, but think about what one vector can express. There's a hard ceiling. The number of distinct things you can rank with a single point is capped by how many dimensions that point has.
That's the bottleneck argument. And it's real. It's not their result. It's a known theoretical limit. If the answer depends on some tiny local detail buried in a long document, the squashed summary can just lose it.
That's the example that sold me. They build a stress test. A grid of little chart panels, each one pairs a code with a colored marker. And then a fake document with the exact same codes, the exact same markers, but shuffled. Wrong pairings.
So globally, the two documents are identical. Same ingredients.
Same everything. The only difference is which code goes with which marker. And the squash cyber search? It picks the right document worse than a coin flip.
Below chance. Because the summary records this document has these codes and these markers, and that's true of both. It never encoded who's paired with whom.
But the per word internal states, the stuff that got thrown away, those still know. If you compare those directly, it jumps from worse than a coin to clearly better than half.
So the information was never gone. It was sitting in the hidden states the whole time. The pooling step just didn't carry it forward.
Right. And here's the part I want you to push on. Why are those leftover states even usable? Nobody trained them to be search vectors.
That's the actual contribution, and it's a nice argument. When you train one of these models, the loss only touches the final summary token. On paper, that's the only thing being supervised.
But
the summary token is computed from all the other tokens, through attention, through the residual stream. So when the gradient flows back to fix the summary, it flows through every word underneath it.
So they get shaped too, without anyone aiming at them.
Implicitly. And because the training objective is cosine similarity, angle between vectors, the leftover states get organized in that same geometry, which means you can do cosine matching on them directly. They're already in the right coordinate system.
That's the elegant bit. You don't convert anything. You don't add a layer. You just start comparing the pieces you were already computing.
This is an old idea wearing new clothes, though. Late interaction, comparing the fine-grained pieces of two things instead of one squashed summary. That's been around in text search for years. Match each query word to its best partner in the document, add it up.
They're not claiming the technique is new. They're claiming you don't need a special model to do it. The plain single vector models everyone already runs. The leftover states are good enough to do it on, untouched.
And the honest move in the paper, they don't throw the summary away. They add the fine-grained score on top of the global one. Global compatibility plus local evidence.
Why keep both?
Because the summary is still a strong, robust signal for, is this broadly about the right thing? The fine-grained part catches the detail it missed. They complement each other. Where it's purely local, that toy grid, adding the global score actually hurts, and they say so.
They flagged that themselves. That's the rigor I liked.
It is. Now the catch. What's the cost at search time? Because matching every piece against every piece is not free.
It's more expensive than comparing 2 points. That's the honest trade-off. But you pay it once at the end, on a short list, not across the whole index.
And it doesn't help everywhere. They're explicit. This is for finding things where the answer hides in local detail. For course what category is this tasks, the squashed summary was already fine, and the fine-grained matching just adds noise.
Right, it's not a universal upgrade. It's a you've been leaving local evidence on the floor upgrade.
And if you're willing to spend a little under 2 hours on modest hardware, train one small readout on top of a frozen model. A plain single vector model catches up to the specialized multi-vector ones. People spend much longer building.
That's the headline for me. Not new method beats old method. It's the thing you already have was smarter than you treated it. You just stopped listening after the summary.
Which is a good wild card. No grand thesis. Just go check what your model already knows before you train a new one.
Pick the evidence back up off the floor. Different flavor of wild card. This one trained a top-tier research agent, the kind that browses the web for you and writes a sourced report, on tasks that nobody ever actually asked, entirely made up.
Made up by what?
By another model. The whole training set is synthetic. No human wrote the questions. No human graded the answers. And the result holds its own against the closed proprietary research agents from the big labs.
That sentence has a trap in it. Trained on made-up tasks usually means trained on garbage. How do they grade a made-up task? That's the part that breaks.
That's exactly the part they solved, and it's clever. The grading is the hard problem, not the question.
Walk me through it.
So a deep research agent does 3 different jobs. 1. Go dig up a specific hard-to-find fact across a bunch of pages. 2. Write a long readable report that pulls many sources together. 3. Back up every claim with a real citation that actually says what you claim.
And those are graded completely differently. The fact has one right answer. The report doesn't.
Right, and that's why most prior agents are lopsided. The ones trained on find the obscure fact data are great at fact hunting and weak at writing. They overfit to their own recipe.
So how do you build one training format that covers all 3?
A grading tree. For every task, instead of one answer, you generate a tree of criteria. The top is overall quality. It branches into sub-goals. The leaves are tiny yes or no checks. Does it cite a source here? Is this number right? Did it cover this angle?
So a single answer isn't right or wrong. It's you satisfied 11 of these 15 little requirements.
Right. And that gives you a partial score instead of pass-fail, which matters enormously for training, because pass-fail tells the model almost nothing when it's failing most of the time.
That's the real win, and people will skim past it. A binary reward, right or wrong, is a terrible teacher on hard tasks. You get a wall of zeros and no gradient toward less wrong. The tree gives you you're getting warmer.
Warmer in specific named ways.
Fine. So where did the task come from? Because the tree is the grader. You still need the question.
They seed it from trending search topics, real things people are looking up. Then they point a capable model at the open web, let it browse around, and have it invent a question whose answer it can pin to verifiable constraints. The tree falls out of that.
And here's where I get nervous. The same family of models is writing the question, building the grading tree, and later grading the student. That's a closed loop. If the grader has a blind spot, the student learns the blind spot and nobody notices.
That's the right worry. They lean hard on filtering to fight it. They throw out most of what they generate. For the fact-based tasks, they start with 17,000 and keep under 6. If the tree can't be turned into a clean, runnable check, it's gone.
So the rigor isn't trust the model. It's generate a flood and keep only the few that survive strict verification. That I'll buy more.
And for the factual ones, the grade isn't a model's opinion. They turn the tree into an actual program. Code that checks the answer, no vibes.
That's a meaningful distinction. A script that verifies a date or a number is reproducible. A model judging an essay is not. What about the essays then? The reports?
Those they can't run as code. So they write a reference report first, then have a judge read the agent's report and the reference side by side and score which is better. Criterion by criterion.
Side by side matters. Did they say why?
They did, and it's from their failure log, which is my favorite section. They first tried grading reports alone, no reference. The judge handed out near-perfect scores to basically everything. Half the answers got top marks.
Of course it did. A judge with no baseline just flatters the work in front of it. There's no scale.
Then they swung the other way, head-to-head against a strong teacher report, and early on their model was worse than the teacher every time, so the judge said, lose, 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 and the score collapsed to all zeros. Useless again.
Both ends dead. One floor, one ceiling, no signal in between. So the trick is comparing against a reference but on a graded scale, not just win-lose.
Right. A relative score, how close did you come with gradations? That's what finally gave them a usable signal.
I appreciate that they printed the dead ends. Most papers bury those. Tells you the final design was forced by what didn't work. Not picked because it sounded good.
There's one more piece I want to get to, because it's the unglamorous one that probably does the heavy lifting. Memory.
The context problem. A research agent reads dozens of pages. That all piles up and eventually the model drowns in its own notes.
So they add a condenser. When the notes get too big, it compresses them, but into 3 labeled buckets. Trusted. Facts I checked against a real source. Untrusted. Claims something else contradicted with the reason. Uncertain. Maybe true. Here's the exact next step to confirm it.
That's nicer than a flat summary. It's not, here's what I read. It's, here's what I know, here's what I doubt, here's what I still owe myself. The agent can pick up cold and keep going.
And it means it doesn't refetch the same page 10 times. It trusts its own verified notes.
Now, does it actually work, or is this an architecture diagram in search of a result?
It works. The big version lands around the open competitors at its size and reaches the proprietary research agents on several of the hard tests. And the genuinely surprising bit, even a tiny version of it, small enough to run privately, is strong at the fact-hunting jobs. Matches systems many times its size on those.
With the obvious asterisk that the tiny one falls apart on the long report writing.
They say so plainly, small models can find facts. Synthesizing a real report still wants scale.
Then here's my one-line takeaway, and it's a Friday-shaped one. Everyone's going to read trained on fake tasks and here trained on junk. Flip it. Once your ruler can say warmer instead of just no, it stops mattering who wrote the question.
So the made-up tasks aren't the compromise. They're the unlock.
The questions were never the scarce thing. A good enough ruler makes them free.
Invent the test, and the practice problems write themselves.
Which is either the future of training data or a hall of mirrors. Ask me again in a year.
Okay, 12 wildcards, no thread. Did one stick with you more than the rest?
The physics one, the CAD Agents. Not because it worked, because it didn't, and the paper was honest about it. Most of the class failed the exam, and instead of hiding that, they made the exam the point.
The grader's worth more than the score.
That's the line I'm taking home. You learn more from the test that fails everyone than the one everyone passes.
Mine's the sleep paper. Not because it's the most important, it's probably not. But the idea that a model might need downtime to consolidate what it learned, the way we do, and that skipping it degrades the thing.
You like it because it's a little uncanny.
I like it because it's the kind of idea that sounds like a metaphor right up until someone measures it.
And then it's not a metaphor.
and then it's a result. That's the whole reason a wildcard day exists. The papers that don't fit the theme are sometimes the ones doing the genuinely new thing. There's no slot for them yet, because nobody's built the slot.
The frontier model running on a tenth of itself will get the headlines.
It should. It's a real release.
But the one that sticks is the weird one. It always is.
That's the feed. No thread, no apology.
That's the feed.